Hello, good citizen. My name is Batman. I will try to make things a little bit easier for you today. Basically, after we have talked about the concept of the derivative, we can take stock about what we know about derivatives, and our conceptual knowledge is considerable. I mean, we know that the derivative is the slope of the tangent line. We know that a positive derivative means that the function is increasing. We know that a negative derivative means that the function is decreasing. And we know that a positive second derivative means the function is concave up, a negative second derivative means the function is concave down. We know that a zero derivative gives us a critical point, and we know that the derivative of a position function is the velocity. The one thing that we haven't talked about so far is how to compute those derivatives more easily, and certainly that was intentional because working with these difference quotients, first of all, reminds us a little bit more as to where derivatives come from. Second of all, it practices some more of those algebra skills that I certainly believe we need to have in order to make things more easy down the road. But at some point in time, you really realize that, well, you need to have some kind of shortcuts, and that's where differentiation rules come in. And the first rule that we're going to talk about in this module is the power rule, which is the subject of this presentation. So, well, what is the derivative of a polynomial? Specifically, what's the derivative of a monomial of the form x to the n? You've already taken some derivatives using difference quotients, derivatives of square polynomials, probably also of some cubic polynomials. What's the underlying principle? Well, whenever you want to determine the derivative of a function that you don't already know, you have to go back to those difference quotients. They're not going to go away, but the advantage is this time we're just going to use them to derive a rule, and after that we're not going to mess with them anymore. So the definition of the derivative is always the same. The limit as h goes to 0 of f of x plus h minus f of x divided by h. And if you do that with f of x being x to the n, you end up with x plus h to the n minus x to the n divided by h, limit as h goes to 0. And we know from experience now how this goes. We somehow have to work out these parentheses, and as soon as we have that, hopefully the x to the n will cancel, then hopefully the h will cancel, and we will end up with what that derivative is. Okay, how do you multiply out x plus h to the n? Well, that's where you go to what is called the binomial theorem, and what you may have seen, and which is called Pascal's triangle, because basically when you work out a binomial, you basically write down your x's in decreasing powers, your h's in increasing powers. So you start with x to the n, then you go with x to the n minus 1 times h, x to the n minus 2 times h squared, and so on, up until you have x squared times h to the n minus 2, x times h to the n minus 1, and h to the n. And the coefficients are obtained via Pascal's triangle, which is something where you put ones on two diagonals, and then every next row's entries that are not on these two diagonals are just the sum of the two entries above it. So the first row in Pascal's triangle is 1, 2, 1, and that is the sequence of coefficients for multiplying out x plus h squared. It's x squared plus 2xh plus h squared. The next row is x cubed plus 3x squared h plus 3xh squared plus h cubed. Hang on just a minute, somebody just knocked. And I'm back. Okay, this Pascal's triangle gives you the coefficients for the expansion of a binomial. And so the fourth row would be 1 plus 3 gives you 4, 3 plus 3 gives you 6, 3 plus 1 gives you 4 again. And of course the arithmetic is terribly exciting here. You can see that it really works out. Every coefficient is the sum of the adjacent ones that are above it. That keeps going like that, and it can be proved that these really are the coefficients that are needed to expand a binomial. Now let's look at this. As we expand a binomial, the first term will always be x to the n. The second term will be x to the n minus 1 times h times whatever this coefficient is, and you can see for a second power the coefficient is 2, for a third power the coefficient is 3, for the fourth power the coefficient is 4, for a fifth power the coefficient is 5, and so on and so on. Well, for an nth power the coefficient will probably be n, and that is indeed the case. And all the other terms have an h squared at least, and if it's got an h squared, we know that from the experience we've got with difference quotients, most likely it's going to go away, and that's indeed the case. So what we can say is that this is the limit as h goes to 0 of x to the n plus n, that coefficient from Pascal's triangle, times x to the n minus 1 h, which is how the pattern for in which we're expanding the binomial, plus h squared times more terms minus x to the n. Okay, well, the x to the n's cancel, so we end up with a limit as h goes to 0, n x to the n minus 1, h plus h squared times more terms. Now, remember, better safe than sorry, factor out the h. You end up with a limit as h goes to 0, n x to the n minus 1 plus h times some more terms, but there are only finitely many of those, and so as h goes to 0, this part back here goes away. And that means the limit overall is n times x to the n minus 1. Okay, so that is the power rule. Other things that we have to deal with, especially in coefficients, are sums and constant multiples. Well, the derivative of a sum, again, we just have to write down the difference quotient, and we realize that f plus g of x plus h, that is f of x plus h plus g of x plus h, f plus g of x is f of x plus g of x, and we pushed in the negative sign. If we resort that and put the f's and the g's together, we end up with the limit as h goes to 0, f of x plus h minus f of x plus g of x plus h minus g of x divided by h. And that's two separate difference quotients, one for f and one for g. And so this ends up being the derivative of f plus the derivative of g. Exponential functions are another kind of function that we may run across early on, and the derivative is fairly easy to work out if we're willing to use graphical evidence for one of the limits. So the derivative of the exponential function is, of course, the limit as h goes to 0, e to the x plus h minus e to the x divided by h. And remember that if you've got a sum in the exponent, that is just the same as a product in the basis. So this is the limit as h goes to 0, e to the x times e to the h minus e to the x. And this time we can actually, well, we can't factor out an h, but we can factor out e to the x. So this is e to the x, because that doesn't depend on h, times the limit as h goes to 0, e to the h minus 1 divided by h. And that limit formally is actually quite challenging to compute, but graphical evidence suggests that when you plot the function e to the h minus 1 divided by h near 1, that then you end up with a limit of 1, and that is indeed the case. And that means that the derivative of the exponential function is 1. Okay, so the theorem that sums up these differentiation rules, first of all, we have the power rule, which tells us that for every rational exponent, we have that the derivative with respect to x of x to the r is r times x to the r minus 1. Now, the derivation that we've seen only worked for positive integer exponents, but it turns out with some more algebraic finesse that we're not going to worry about in this presentation at least, you can prove this for every rational number, and then with some more machinery, you can actually prove it for every real exponent. We also have a theorem that talks about how to deal with combinations of functions. If you have two functions, f and g, that are differentiable at x, and if c is a real number, well, then the derivative of the sum is the sum of the derivatives. The derivative of the difference is the difference of the derivatives. And the derivative of a product of the function with a constant is just the constant times that derivative. And finally, the derivative of the exponential function is the exponential function itself. These results, just summed up here, allow us to work out derivatives of all sorts of functions, and certainly, first of all, the derivatives of polynomials. And if the derivations so far weren't quite your cup of tea, well, now it's going to get really applied, and that's certainly what we're shooting for, mostly in a calculus class. Okay, so let's first take care of the symbolic basics. If we are supposed to find the derivative of a function like 4x cubed plus 3 over x squared minus 5 times the third root of x, well, we just say we have to find this derivative, but we realize that the only term we can tackle directly is the 4x cubed. This second term and this third term aren't written as a power, so we need to use what we know from algebra to realize that 3 over x squared is nothing but 3 times x to the minus 2. That's the only change that just happened. And we also know that 5 times the third root of x is nothing else but 5 times x to the third. That's the only change that happened. In this transition, you can see we still have the 4x cubed. We have the 3 over x squared in the form 3 times x to the negative 2. And we have the 5 times third root of x in the form 5x to the 1/3. And you really want to be able to translate fluently between these notations. That will make you that much more efficient as you are doing your computations. What comes now probably has too many steps in between, and we're only going to do it in this level of detail once, but nonetheless, you realize that, well, if you've got a derivative of a sum or a difference, well, that's just the derivatives of the individual terms with the appropriate signs in between. And we know that if you have a constant in front of a function inside the derivative, then the constant can be pulled out, and that can happen for the 4x cubed, it can happen for the 3x to the negative 2, and it can happen for the 5x to the 1/3. And now these terms here, these three terms, can be handled with the power rule. So the first term is 4 times 3x squared, right? You bring the exponent down, that's the 3, copy the x, and then subtract 1 from the exponent, and that's your new exponent. You do the same thing here. You end up with 3 times negative 2 comes from the exponent. Then you've got the x, and then negative 2 minus 1 is negative 3. And finally, the x to the 1/3, that's where we have to deal with fractions. Negative 5 times, exponent comes down, 1/3, times x to the exponent minus 1. Well, 1/3 minus 1 is negative 2/3. And then we can just simplify. 4 times 3 is 12, so we end up with 12x squared. We end up with negative 6x to the negative 3, and we end up with minus 5/3 x to the negative 2/3. And if we want to go back to the notation of how the problem was posed, then we would say this is 12x squared minus 6 over x cubed minus 5 over 3 times third root of x squared. It's in the denominator because we've got a negative exponent. The x is squared because we've got a 2 in the numerator of the exponent, and we have a third root because we've got a 3 in the denominator of the exponent. All right, now we can find tangent lines for arbitrarily complicated or near arbitrarily complicated functions. For example, for the polynomial f of x equals negative x cubed plus 5x plus 1 at x equals 1. You take the derivative. Well, that is negative. The derivative of x cubed is 3x squared. The derivative of 5x is 5. That's the one where x is x to the first, right? So you end up as a derivative having 1 times x to the 0th, which is, of course, just 1. And the derivative of a constant is 0. Basically, you could say here that 1 is 1 times x to the 0th, and when the 0 comes down, well, then you end up with 0 overall. Okay, how do you get the equation of the tangent line? Well, you need the slope at the point, so you plug in 1 into your derivative. Well, that's negative 3 times 1 squared plus 5, that's just 2. You also need the point. Well, f of 1 is negative 1 cubed plus 5 times 1 plus 1, so that should be 5, right? And now remember that the equation of a straight line is always y equals mx plus b. We have m, that's the slope, that's the 2. We have x, that is 1. And we have y, which is this 5. So we end up with 5 equals 2 times 1 plus b. And that gives us b equals 3. And that means that the equation of the tangent line is y equals 2x plus 3. And just as we have seen in earlier presentations, we can just go ahead and graph that function and graph the line that we assume to be the tangent line. And as long as that tangent line really just barely touches and is tangential visually to the function at the point where we wanted to compute the tangent line, everything's fine, which it is here. Okay, we can also determine where fairly complicated functions are increasing or decreasing, such as this polynomial 3x to the 4th plus 8x cubed plus 6x squared minus 3. That's certainly something that, yeah, in principle we can work it out with difference quotients, but to be quite honest, I would not want to. So what do we have to remember conceptually? Conceptually, a positive derivative means that the function is increasing. A negative derivative means that the function is decreasing. That almost becomes a mantra as you're going through this stuff, but, well, we remember that it is true, and we just want to bond it closely enough to our consciousness that we can rely on that as we do the computations. And so, well, first thing we need is the derivative. Well, the derivative of 3x to the 4th, the 4 comes down, and then you have an x cubed, so that should be 12x cubed, right? The derivative of 8x cubed, the 3 comes down, giving us a 24, and x cubed, 3 minus 1 then is 2, so we end up with 24x squared. The derivative of 6x squared, the 2 comes down, giving us a 12, and x to the 2 minus 1 is x, so we get 12x. And the derivative of the negative 3 is 0, so that just goes away. And, well, now we need the zeros, right? Because if we want to know where the function is increasing or decreasing, we need to know where it changes its signs. And that means, first of all, we want to factor out anything that's obvious. And these terms here have a 12x in common. I've taken that out. And x squared plus 2x plus 1, you could work that with the quadratic formula. Or this is actually a perfect square. And I think I just accidentally saw that factorization, and if you see that factorization, you just work it out, make sure that it's right. X plus 1 squared, yes, that's x squared plus 2x plus 1. But as soon as you know that, you just have the factorization, and you find the zeros from the factorization by setting things equal to 0. Well, the first term is 0 when x is equal to 0. The second term is 0 when x is negative 1. And that means we can now set up our number line. We have two cut points, negative 1 and 0. And in order to find where the derivative is positive or negative, we need to find checkpoints, one to the left of negative 1, one in between, and one to the right of negative 1. And I've chosen here negative 2, 1 convenient points to the left and to the right. And, well, there really is no convenient point between negative 1 and 0. They're all fractions. And I just chose negative 1/2. Now we need to find out the sign of the derivative at all these points. And, well, let's see. The derivative at negative 2. At negative 2, we end up with negative 2 cubed, which is negative 8 times 12. Well, negative 8 times 12 is what? That would be negative 96. And then you get negative 2 times 12 here. That gives you negative 24, so negative 96 from here plus negative 24 from here gives you negative 120. And negative 2 squared is 4. Well, 4 times 24 is 96. So you end up with a negative 96, a positive 96, and negative 24. The derivative is negative at negative 2. And that means the derivative is negative on the whole interval from negative infinity to negative 1. Similarly, at negative 1/2, let me just peek and see if I first handle 1 and then negative 1/2. I first handle negative 1/2. Okay, so how does negative 1/2 go? Apparently it ends up being negative. Well, I can plug it in here, and that does work out. It's of course a lot of acrobatics with numbers and with fractions. If I trust my factorization, I can also plug it in here. Well, 12 is positive, negative 1/2 is negative, and negative 1/2 plus 1 quantity squared is positive. So we end up with negative, positive, positive. That's negative, and that's of course what this thing says here also. And at 1, well, we can go either way, and well, the easy computation here, just plugging it into the derivative, is 12 plus 24 plus 12. I don't care what that is. It's a sum of positive numbers, so that's going to be positive. So either way you do it, the trick is this time you plug things into the derivative, and you're only interested in the sign. And if you don't want to deal with all the mental arithmetic, yeah, it's okay to plug that into a calculator if calculators are allowed on your tests. Otherwise, well, use a piece of paper and work it out. It's really not that bad. It's just math. It's just numbers. Okay, we can again check, or we can now interpret this first of all. Derivative being negative means the function is decreasing from negative infinity to negative 1, decreasing from negative 1 to 0, and increasing from 0 to infinity. And we can also check that by just plotting the function and comparing the plot to what we have worked out in our analysis. And here's where it certainly again pays to have things worked out on scale, because then we can compare directly. And here we see there was a potential change at negative 1, but see there's only a saddle point. We get a horizontal tangent line, but the function is decreasing before and after we go through negative 1. And then at 0, this just superimposed a little blue line here that is kind of hard to see, but at 0 we change from decreasing to increasing, and that's exactly what the graph does. So again, we have graphical verification that we have the right result. And again, this is where I'm often a little bit preachy, but I'm not self-conscious about that. This is a way to double-check your work without having to look in the back of the book, without using an oracle. You're using tools that you will have as a working scientist, as a working engineer, as a working mathematician, as a working business individual. And so that then is certainly much more powerful than relying on the back of the book, because, well, there will be no back of the book when you have to solve a problem on the job. Okay, we can also find relative extrema of another rather ugly looking polynomial. And again, well, how do you find relative extrema? You first take the derivative, set it equal to 0, and then find where you're changing from increasing to decreasing or decreasing to increasing. So here, the derivative of negative x to the 4th is negative 4x cubed. The derivative of 4x cubed is 12x squared. The derivative of negative 2x squared is negative 4x. The derivative of 2 is 0. That's something that we're going to go over more and more rapidly, certainly, because these computations should become second nature. We see that there is a 4x that is in common to all these terms. So, and in fact, I even took out the negative sign. So this is negative 4x times x squared from here. Then we've got a 3x, a negative 3x remaining from the middle term, and a 1 remaining from the last term. Note that all the signs change because we factored out a negative term. Now we want to set that equal to 0, and of course when you set negative 4x equal to 0, you get 0. For the other one, it's definitely desirable to use the quadratic formula because the roots turn out to be ugly. And remember, if you see a factorization quickly, there's no penalty in writing it down as long as it's correct. But if you don't see it quickly, then you might as well use the quadratic formula, and that's what we'll do here. So first of all, the first 0 here is 0, and then for x squared minus 3x plus 1 equals 0, I use the quadratic formula. Negative b, negative 3, plus minus square root of b squared, negative 3 squared, minus 4 times a, which is 1, times c, which is 1 also, divided by 2 times 1. And so that ends up giving us 3 plus minus square root of 9 minus 4, so square root of 5 divided by 2. Yeah, 3 plus minus square root of 5 divided by 2. And that's something, look, I've never said calculators are the devil's work. Calculators are useful, and if I want to know a decimal for these numbers, I work it out with a calculator, and the numbers are approximately 0.3820 and 2.6180. Now, there are two possibilities. We can use the second derivative test, or we can just do the sign testing, and the sign testing is a bit more reliable, and so that's what I'm going to do here. So we set ourselves up with a number line. We've got 3 cut points, 0, then the 0.3820, which is 3 minus root 5 over 2, and 2.6180, which is 3 plus root 5 over 2. Note that this is not quite to scale because, well, I need to squeeze a cut point in here, and I can't do that if I put it where 0.2, approximately 0.4 would be if this is supposed to be 2.6. But nonetheless, I need 4 cut points here, 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 and here. Convenient point to the left of 0 is negative 1. Convenient point between 0 and 3 minus root 5 over 2 is 1/10. I mean, they're all pretty ugly there. Convenient point between these two difficult ones is probably 1. And a convenient point to the right of 2.6 would be 3. Now we need to find out what f prime does. Well, f prime is positive at negative 1, and that's most easily seen by just plugging it in, I guess. Negative 1 cubed is negative 1, so you get negative 4 times negative 1, which is 5. Negative 1 squared is 1, so you end up with 4. Negative 4 times 1 is not, negative 4 times negative 1 is not 5, it's 4. 12 times 1 is 12, so you end up with 16, and then I don't care if that's negative or positive, it's either plus 4 or minus 4, and 16 plus or minus 4 ends up being positive, right? When we're looking at the 1/10, well, let's see, how can I finagle that one? I think I'd want to look at the factored form here. 1/10 is positive, negative 4 is negative, so we've got a negative and a positive, and then we've got 1/10 squared, which is really tiny, minus 3/10 plus 1. Well, so that's a bunch of tiny stuff plus 1, so that ought to be positive also, so we've got negative, positive, positive, and that ends up being negative, good. At 1, well, negative 4 plus 12 minus 4, that ends up being 4, that's positive. And at 3, well, at 3, how do we handle this? 3 cubed is 27 times negative 4, ends up being negative 108. 3 squared is 9 times 12, ends up being 108 also, so negative 108 plus 108 goes away. And then we've got negative 4 times 3, which is negative 12, that ends up being negative again. And so the derivative is positive, negative, which means the function is increasing, decreasing, increasing, and decreasing again. And again, we can double check that. Okay, first of all, because we're looking for the relative extrema, it's always good to just answer that with a sentence. There are relative maxima at x0 equals 0 and at x2 equals 3 plus root 5 over 2, because those are the places where we change from increasing to decreasing at 0 and from increasing to decreasing at 3 plus root 5 over 2. And there is a relative maximum at x1 equals 3 minus root 5 over 2, because that's where we go from decreasing to increasing. That's where the function goes down and comes back up. Okay, we can double check that again by just plotting the function and comparing the plot with what we have worked out on that number line. Now remember, this was not quite to scale, but the points where things change are 0 here. That's where it changed from increasing to decreasing. That's a very subtle relative maximum here, but we can see that this is a little bit lower than that. So yes, there is a subtle relative maximum there. Then we've got the 3 minus root 5 over 2. That actually was the 0.38. And we see there's a very subtle relative minimum here. If you don't see that well enough, go ahead and plot this function and zoom in on this area on your graphing calculator or your computer. And then at 3 plus root 5 over 2, we've got a very pronounced and very easy to see relative maximum. And that's really all the extrema that we have of this function, because a fourth order polynomial comes from minus infinity, goes to plus, and goes back to minus infinity if the leading term is negative, and it can only wiggle around so many times, namely it can have at most 3 turnaround points, and we found them all. Okay, we can also find where a function is concave up or down. That's where we have to find second derivatives, and again, that's something that we wouldn't want to do with difference quotients. And what do we remember conceptually? A positive second derivative means the function is concave up, a negative second derivative means that the function is concave down. And so we can take the derivative. It's 3x squared minus 8x minus 1, just from here, and that computation is now straight power rule, using it with some mental computation. Second derivative is 6x minus 8. It's the derivative of 3x squared minus 8x minus 1. And we have to set that equal to 0, which gives us that x is supposed to be 8 over 6, which is, of course, 4/3. So this time we only have one cut point, which is 4/3. Choose a checkpoint to the left and to the right, 0 and 2 most likely. This time we plug that into the second derivative, because we're interested in where the function is concave up or down, right? We're not interested in where the function is increasing or decreasing. And the way to remember that typically is that these checkpoints need to be plugged into exactly the derivative that gave us the cut points, which is the 6x minus 8 in this case. And well, at 0, that's negative 8, which means the second derivative will be negative from negative infinity to 4/3. And at 2, we get 12 minus 8, which is 4, so the second derivative will be positive from 4/3 to infinity. Okay, that means the function is concave down from negative infinity to 4/3, and concave up from 4/3 to infinity. If you want to, you can also write that out as a sentence, certainly. And we can double check it again. If we just graph the function and put what we have computed analytically underneath, we see that the change is at 4/3. It didn't quite line up right here. That's quite a pain to actually make line up correctly, and I just didn't have the patience to spend another 15 minutes to half hour to just make sure this absolutely lines up right. Okay, maybe it was just a couple of minutes, but it takes quite a while to make these slides, so I didn't do it. But we can see our analytical result certainly is consistent with what the picture does. The function is concave down, and then it is concave up. And that, in a way, is the predictive power of mathematics that we certainly are going to put in good use in our applications of calculus. Finally, well, again, we also want to work with parameters, and then this is a sermon that you've heard a couple of times. Ultimately, we'll work with problems that involve more than one variable. For example, you already see this in your physics and chemistry classes. The universal gas law has 5 letters. 4 of them are variables. 1 of them is a constant. And if you work with the van der Waals equation, which is a correction to that, you have even more variables to deal with. But it is an more accurate model, so we have to work with that at times. Harmonic oscillators, which you may have seen in physics, the formula for the frequency includes the spring constant and the mass, which is at least 2 variables on the right-hand side, and the differential equation, which you will see in a differential equations class, and or in advanced physics classes, involves 3 variables, mass, friction coefficient, and the spring constant, plus an unknown right-hand side, which may be a function. So there's a lot of stuff out there that really we need to be prepared for, and that uses more than just y equals f of x. In terms of working with numbers, remember, I'd rather work with pi than with all those digits. And, well, then also in making our solutions applicable to more problems, the graph of any quadratic function is described with this, and our example actually will talk about quadratic functions when this stuff is multiplied out. And in optimization, we can optimize the surface area of a rectangular box for any fixed volume, rather than just for one number that is given, and that then again gives us an optimal result that can be adjusted if you want to have volumes of boxes of different volumes. Finally, again, let's remind ourselves, even though the routine problems ultimately are sort of our happy place in mathematics, that's the stuff that works, and there's nothing wrong with being happy to solve certain problems, because, I mean, what we consider routine problems at this stage were not routine problems when we were just looking at it in terms of algebra. Finding extrema is not a routine problem in algebra. In many cases, in fact, it is impossible, but we are rapidly ramping up our capabilities here. And so, hey, I mean, being able to solve those problems, that's good. It's not something to be poo-pooed or anything like that, but let's always keep our eyes on the fact that there's more stuff out there. And so we cannot afford to stagnate. And again, routine problems, and ultimately we solve them with computers, and what we do is we parameterize them and program them. Okay, so, and finally we can also gain deeper insights into by solving harder problems. And for example here, this is a problem where we say, well, find the critical points of the function f of x equals ax squared plus bx plus c. And you may rightly say, I already know those problems because the vertex formula tells me where the vertex is, and the vertex is the only critical point of these things. So basically another way to formulate this is, this problem will give us the answer why the vertex formula for a quadratic is the way it is. But what we have to do, and here's where I personally, I typically don't memorize the vertex formula. I know how to take derivatives, and that's good enough. The derivative of ax squared plus bx plus c is 2ax plus b, right? You keep the constant. The derivative of x squared is 2x, so you get 2ax. The derivative of number times x is always just a number, so you just get the b here. And the derivative of a constant c is 0, so that goes away. You set that equal to 0. You end up with x being negative b over 2a, right? The negative b comes over, then you divide by 2a. And that critical point is a vertex either way, because if we're now doing our sign analysis, we've got one cut point where things change. And here's where things get a little bit problematic, because we have to find a checkpoint to the left and a checkpoint to the right. And basically what I would do is I would just take negative b over 2a minus 1 and negative b over 2a plus 1. Those are guaranteed to be to the left and to the right of negative b over 2a. And if we, whoops, I'm pushing the wrong button. If we're now looking at the sign of the derivative in those places, well, to the left of negative b over 2a, well, negative b over 2a makes this whole expression equal to 0. And if we then have a minus 1 in there, we end up with just negative 2a. So it's going to be negative when a is greater than 0, and positive when a is smaller than 0. Similarly, to the right, if we plug in negative b over 2a, that will make this whole expression equal to 0. Then we plug in the 1 into the x, we end up with 2a. And 2a is positive when a is greater than 0, and negative when a is smaller than 0. And so either way, the derivative changes from negative to positive if a is greater than 0, and from positive to negative if a is smaller than 0. And that means it's a vertex either way. We're changing from decreasing to increasing if a is greater than 0, and from increasing to decreasing if a is smaller than 0. And that is in fact the picture that you also have of a quadratic. If you have a negative leading coefficient, the thing goes first up and then goes back down. And if you've got a positive leading coefficient, the function goes down and then back up. All right, so what we've got now is we have a tool that allows us to compute derivatives that we in principle could solve with difference quotients, but really I would not want to do it. And we're going to put that tool to good use. We're going to talk in two separate presentations about graphing and about optimization. These are important conceptual topics that deserve to be treated separately. And then for the rest of this module, we're going to just derive more differentiation formulas and demonstrate how they work in action. Until then, I am Batman.